Hi, it's Paul Andersen, and this is Crosscutting Concept 1, Patterns. This is the first of 7 cross-cutting concepts. And you might think, as a teacher, why do we have to teach things like patterns and cause and effect and structure and function? Don't students just understand these things? And what we're finding is no. It's important that we explicitly teach them how to use terms like patterns and pattern recognition so they can use them throughout their whole education. Because terms like patterns, concepts like patterns are going to be found in chemistry, in biology, in physics, and engineering. And it's important that we give students the terms that they can use throughout their education. Because patterns are everywhere. We're going to find patterns in a snowflake. We're going to find patterns in nature. We're going to find patterns even in this presentation. I've hidden a pattern in this presentation, and there will be a question mark at the end. Hopefully you can figure out what that question mark stands for. Patterns are important in science and engineering. They're important in science because they initiate questions. They trigger questions. When we see a pattern, we want to explain why it occurs that way or why that pattern exists. And so that can eventually lead to better explanations, and it can eventually lead to scientific theories. In engineering, we'll test things over and over to see if there's a pattern or their failure, or we can use patterns to improve our design. So basically, they're improving solutions to the human's problems. And so we find patterns everywhere. Like I said, we would find them in these beautiful petals of these flowers. We'd find them in the seasonal changes of the weather, and we'd even find them in molecules like the nucleotide sequence in DNA. And so patterns are everywhere, and what we need to do as scientists is to recognize those patterns, to find them. And let me give you a historical example of that. This is Dmitri Mendeleev. He's a famous Russian chemist, and basically he was around in the time where they were discovering atom after atom or element after element, and they were trying to figure out how these things were all related. He also loved playing solitaire. He loved playing cards, and so he was used to laying out cards and trying to find patterns within them. And so he did the same thing with the elements of that time. He wrote down everything we knew about the elements, and then he just started laying them out on a table and organizing all the cards, putting them all together. And what he found is that patterns started to emerge. And so you can see here that boron, carbon, nitrogen, oxygen, and fluorine are all ordered according to their atomic weight. And what he found is that we started to see horizontal and vertical properties start to emerge, and this eventually led to the periodic table. He was the creator of our first periodic table, and we wouldn't have gotten there if we wouldn't have been able to recognize these patterns. Patterns eventually, when we start to organize them, it leads to a process called classification. So we try to put order in chaos or order these patterns. And so if you look at the night sky, you'll see stars everywhere, but their patterns start to emerge if we start to classify it. And so back in time, we used to put the stars in order, and then we would have constellations that would give us a way to remember where the stars are, and we had stories that came from them, like Leo the lion. But when we really started studying astronomy, we got more detailed in our classification. And so one of the most famous ways that we classify stars is according to the HR diagram. So basically on one side, you're going to put the color of the light, and that tells us a lot about the temperature. And on the other side, the luminosity, in other words, how bright they are. And what you find is that patterns start to emerge just from these two things, temperature and luminosity. And we can order our stars along this HR diagram. And so we can put giants here, and the sun, I think, is like a yellow dwarf, but it'll eventually get bigger, envelop the Earth, and eventually become a white dwarf. And so we can see stellar evolution as well. And so patterns start to emerge when we classify data points or classify phenomena according to some arbitrary category. In engineering, it's important that we start to use classification and pattern recognition as well. And so product testing is an important thing that we do. And so this is fire testing of wood to see if it hits the standards of a housing district in California. And so we're taking a design and we're testing it over and over and over again, looking for patterns. Is there pattern in their failure or ways that we can improve the design? And we can even design solutions this way. So we could look at energy consumption throughout the whole year, and then we can design a power grid so it's more efficient in the way that we're making use of energy. And so what is the goal in science education? It is to get our students to recognize patterns, to classify those patterns, and then even to evaluate those patterns. And so what's the progression? In other words, how do you teach this? How do you get students in elementary school using the term pattern and pattern recognition? In other words, throwing darts at a dartboard and getting better and better and better over time. And so a good way to start is to start them collecting data. And so you could look at the seasons. You could look at the daily temperature and have them recognize patterns. Or you could even start with the phases of the moon. Most people don't know that the moon is actually visible during a lot of the day. And so you could have the students sketch the phases of the moon, and then you could use that to predict what the next phase of the moon is going to be like, or what's the temperature going to be like tomorrow. So they're looking at patterns and then trying to predict from those. You could also have them look at actual classification in biology. So how do we classify animals? How do we classify plants? How do we put them in these different taxonomic orders? And it's a really fun classroom activity. I always started when I was teaching middle school with just having students throw one of their shoes out on the floor, and then we have to classify them. Now you can't use the size of the shoe, but classifying them. How can we break those into 2 groups and more groups and more groups? How can we make order out of this chaos, or how can we find the patterns within the shoes on the floor? And as you move through middle school, we could look at the patterns of the molecules, and so how are atoms organized into molecules, and so what type of patterns start to emerge and what chemical patterns start to emerge as well. And we also want to, as we move into high school, to evaluate those patterns. In other words, if you were to ask students to classify these 2 insects, they would put them very close to each other, the pill bug and the pill millipede. They might think that they're related very closely, or that these 2 plants are going to be related because they look the same. But it's important as we move into high school that just the physical characteristics are not going to tell us much, because these 2 organisms evolved a similar defense to a common threat. And same thing, if you live in a really dry environment, you're going to evolve a plant that looks like that. But it doesn't mean that they're related together. But if we were to look at their DNA, so if we actually look at the DNA of these plants, we'll find that it's quite a bit different. And so that's another pattern that we can look at. And so again, it's important that we teach students how to use pattern recognition to find patterns in the data, to use that to make predictions, and to even evaluate those patterns. And I hope that was helpful. Oh, did you figure out what the question mark stands for? If you did, make sure you put it in the video comments down below. And first one wins nothing except glory. And thanks.